Good morning, everyone. Today I will talk about intrinsic sparse mode decomposition of high-dimensional random fields with its application to stochastic elliptic equations. This is a joint work with Tom Hall and Qing Li. Since the intrinsic sparse mode decomposition can be viewed as a specific form of sparse PCA, I will first review PCA and sparse PCA. Suppose I have a non-random vector kappa, or I have many enough samples for it. The dimension of this random vector MP may be huge, so I want to use principal component analysis to achieve an efficient representation. The procedure is like this. First, we compute its covariance matrix and then do eigenvalue decomposition to get the eigenvalues lambda and the eigenvectors v. Then the optimal Cater approximation of this random vector is this Cater summation, with the principal factors ck to be the projection of this random vector onto the eigenvectors. Similarly, for a random field kappa x omega, where x belongs to a physical domain, which is perhaps some bounded subdomains in a Euclidean space. There is a so-called Kanu-North expansion, which can be viewed as the continuous version of PCA. The procedure is exactly the same, except that now we are dealing with infinite dimensional problems. We first compute the covariance function and then do eigenvalue decomposition of this covariance function, which is a positive semi-definite compact operator. Suppose the eigenvalues are lambda and the eigenfunctions are f, then the optimal Cater approximation of this random field is this Cater summation, and the case principal factors is the projection of this random field onto the case eigenfunction fk. This is the first 10 eigenmodes of this exponential decay random covariance function. PCA and the Q expansion are widely used in many areas. They are good because they need the smallest number of terms to approximate the random field within given error tolerance. And the principal factors are uncorrelated with each other, so we can talk about one factor without referring to others. But PCA or Q expansion also has its drawbacks. Look at this picture. The eigenfunctions fk are typically non-zero everywhere. This leads to difficulties to interpret the principal factors. Does this suggest that all the principal factors have global influence in the entire domain? This does not follow our intuition. You see, for this covariance function, the correlation between two points decays exponentially fast when they depart from each other. Therefore, in fact, we expect to have some hidden random variable behind this covariance function, which has localized influence range and its influence decays exponentially fast, instead of this global influence range. Second, globally the representation is efficient, but locally it is not. We can say that locally we still need the same number of parameters to represent this random field. Therefore, we want to achieve a representation of this random media such that the random factors eta k are uncoordinated with each other, and at the same time, we want the physical modes gkx as sparse as possible. Imposing the uncoordinated requirement, it is sufficient to find a sparse eigenvalue decomposition for this converse function. But of course, this is not eigenvalue decomposition, so we will not call gkx eigenfunction anymore. We will just call it physical mode. And then the question is how to quantify this sparsity. A direct answer is the area of the support. Recall that the support of a function is the set where the function does not vanish. Therefore, we want to minimize the total area of the support of the physical modes, such that the approximation achieves the given error tolerance. Notice that every non-zero point counts in the area of the support. Therefore, this optimization problem has resolution up to every single physical point, which is the highest resolution. However, this highest resolution leads to an extremely high-dimensional optimization problem, and we can say that the objective function area of the support, which is equivalent to the L0 norm of the physical modes, is not convex. Also, the constraint is also not convex. Therefore, this optimization problem is high-dimensional non-convex and seems impossible to solve. But in practice, do we really need such high resolution? Or can we sacrifice some resolution to make this problem trackable or solvable? Before we answer this question, let's review the eigenvalue decompositions. The eigenvalue decomposition can be viewed one of the solutions of this optimization problem, in which we minimize the number of modes needed to achieve the given approximation error. In this problem, every non-zero physical mode counts by 1 equally. Therefore, its resolution is the entire domain, which is the noise resolution. So, how about we think in the middle? Suppose we have a domain decomposition, the physical domain D equal to the disjoint union of the subdomains Pm, and we define the sparseness of a physical mode Gx respect to this domain decomposition as the number of subdomains where the physical mode G does not vanish. We can say that the finer the domain decomposition is, the more accurate the sparseness of this physical mode will approximate its area of support. Look at this picture. We partition this entire domain into 4 subdomains. The red mode is non-zero in the first 2 subdomains, therefore its sparseness is 2. Similarly, the blue mode has sparseness 3. We also define the quantity dm, which is called local dimension, as the number of non-zero modes on the subdomain Pm. For the first subdomain, only the red mode is non-zero there, so it has local dimension 1. And for the second subdomain, both the red mode and the blue mode are non-zero there, so it has local dimension 2. it is easy to say that the summation of the sparsity equals to the summation of local dimensions. Therefore, instead of minimizing the total area of the support, we want to minimize the total sparsity or the total local dimensions, subject to the constraints that our approximation achieves the given error tolerance. We can say that this problem has resolution up to the domain decomposition, which is an intermediate resolution. Surprisingly, if the covariance function and the domain decomposition have some good interaction, we can rarely solve this optimization problem efficiently, and we call the optimizer G star as the intrinsic sparse mode of this covariance function. Let's go to the solution of this optimization problem. Follow the flow down of compressed sensing. Let's look at the noiseless case first, in which we can get exact recovery. For the noiseless case, the constraint becomes an equation. Recall that on the subdomain Pm, we only have Dm non-zero modes. Therefore, the local covariance function, cov_m, can be represented as this Dm term summation. At the same time, we can also do eigenvalue decomposition for this local covariance function, and suppose we get the local rank is Km and the local eigenfunctions are Hkm. Because eigenvalue decomposition is the most efficient representation. Therefore, the local dimension Dm is greater than or at least equals to Km. We made the following regular sparse assumption, which says there exists an optimizer G star that achieves the theoretical local minimum dimension, which is Dm star equals to Km. After this assumption, we already know that the minimum value of this optimization problem is the summation of the local rank, but we still don't know how to recover the intrinsic sparse modes G star. Let's first stack the local eigenfunctions H together to form this capital H, which can be proved to span the range space of the covariance function. Then, there exists a matrix lambda such that the covariance function can be represented as H lambda H transpose. We call this matrix lambda as the coordination matrix between patches. Then, this theory tells us how to recover the intrinsic sparse modes G star. Given that the covariance function is regular sparse on the domain decomposition P, and suppose G star is one of the optimizers, then we know that lambda has non-zero eigenvalues Sk star, which is exactly the sparseness of the intrinsic sparse modes. Second, there exists one version of lambda's eigenvalue decomposition, lambda equals to omega star transpose, such that G star equals to H, the local eigenfunctions, times omega star. There is a direct corollary here. If the coordination matrix lambda does not have repeated eigenvalues, then the intrinsic sparse modes G star can be recovered by G star equals to H times omega star. And for the degenerate case, we designed fast algorithms to recover G star from the eigenspaces omega t. Due to the time limitation, I will not get into the details of proof and the details of algorithm. Let's then look at the bounded noise case, in which we will have some stability results. For the bounded noise case, the covariance function cov hat equals to the scatter summation but plus the noise term n. The L infinity of this noise is bounded by a small quantity epsilon. It can be proved that with the same algorithm, we can obtain an approximation of the intrinsic sparse mode G star hat, which satisfies the distance between the recovered G hat star and the exact intrinsic sparse mode G star is bounded by C times epsilon, where the constant C depends on the local eigenvalues and the local dimensions. Let's look at this exponential decay covariance function again. After our intrinsic sparse mode decomposition, we can get the following intrinsic sparse modes. Let's look at this red triangle mode first. It is only non-zero on 2 subpatches, therefore it has sparseness 2. Also, we have some other physical modes has sparseness 1, but all of them is localized. In total, we use 21 physical modes to achieve an approximation error, 6.5%, and our local dimension is 6. In comparison, the Q expansion used 20 physical modes to achieve the error 6.4%, and its local dimension is 20. Therefore, we rarely achieves a localized representation, and our local dimension is much smaller than the Q expansion. But in fact, we can do more. For realistic problems, random fields may also contain a few global factors. So we want to model the random field as the global part plus the local part. The global part contains a few global factors with their influence function f, and the local part contains many local factors with their influence function g. The corresponding model for the covariance function is a low-rank covariance function L plus a sparse covariance function S. L is low-rank because we assume that we only have a few global factors, and S is sparse because the physical mode G is localized. Obviously, the global part and the local part have different natures and should be dealt with different methods. Therefore, the first step to obtain such a representation is to decompose the covariance function into a low-rank part plus a sparse part, and then we can use eigenvalue decomposition of L to recover the global modes F, and use our intrinsic sparse modes decomposition to S to recover the localized modes G. Fortunately, the matrix decomposition of the covariance function can be obtained by this optimization problem, in which we minimize the nuclear norm of L plus alpha times the L1 norm of S, where both L and S are positive semi-definite. The following corollary from Chandra and his collaborators guarantees exact recovery of L and S from this optimization problem under this strange condition. This condition seems to be mysterious, but in fact what it says is simply the no-rank part L should not be sparse and the sparse part S should not be no-rank. Therefore, they can be identifiable. Let's look at an example. Here, we have two global modes sine and cosine. Also, we have 5 localized modes. The corresponding covariance function looks like this. In the first step, we use our no-rank plus sparse decomposition to get the no-rank part and the sparse part. And then we use eigenvalue decomposition of L to recover the sine and cosine modes. And we use intrinsic sparse mode decomposition of S to recover the localized physical modes. In comparison, Q expansion just mix everything together. All the eigenfunctions are non-zero everywhere. Now let's turn into the applications to stochastic elliptic equations. In petroleum industry and material science, we have the following elliptic equation with random coefficients, and its boundary condition is 0 for simplicity. We want to obtain statistical properties of the solution Ux omega, which is also a random field. Here, the random coefficient kappa x omega is stochastically high-dimensional and has multiple scales. This high-dimensional and heterogeneous property really makes this problem extremely heavy computational cost for existing methods. The typical procedure to solve this problem is first, we want to do media representation. K expansion is used without being challenged for many years, and in fact, it does a good job in low-dimensional problems. But now we are facing high-dimensional problem. As an alternative, our intrinsic sparse mode decomposition can offer us locally low-dimensional representation. Perhaps this can have some benefits. For the second step, we want to solve the parameterized PDE. To solve this parameterized PDE, we first utilize some local solver to construct the local solution space. To effectively construct the local solution space, we only care about the no dimensionality locally, and then we utilize some global solver to patch the local solutions together. Compared to Q expansion, our intrinsic sparse mode decomposition offers us much fewer parameters locally. Therefore, we can expect that perhaps we can get a lot of computational cost saving. Let's look at two examples. In the first example, the random coefficient is a log Gaussian media. The random field beta x omega in this exponential power is Gaussian field with covariance function, the exponential decay covariance function. We already know that for this covariance function, K expansion takes 20 physical modes to achieve 6.4% error, and the no-code dimension is 20. While our intrinsic smart decomposition used 21 physical modes to achieve approximation error 6.5%, and the no-code dimension is only 6. After applying the PDE solver, we get the following result. Look at this picture. This is the error of the mean field. The red line is the method based on K expansion, and the blue line is the method based on our intrinsic spatial decomposition. This picture shows the error of the variance field, and also red represents the K expansion and the blue represents the intrinsic spatial decomposition. We can say that these two methods get approximately the same error. However, let's look at the computational cost. The ratio of the computational cost for these two methods is about 10 to the power 4. Therefore, we rarely achieve a lot of computational cost saving. In the second example, we have high contrast media with inclusions and channels. This is one realization of the random media. This is the channels and this is the inclusions. And this is to model the permeability field underground. So from low-rank spatial decomposition and our intrinsic spatial decomposition, this is one of the global modes recovered, and this is one of the localized modes recovered. After applying the PDE solver, this is one sample solution, and this is the reference solution. We can see that, okay, they match quite well. Also, this is the mean field of the solution and this is the variance field. Both of them are computed from our method. Let's look at the computational cost. For our method, it takes about 2,000 seconds to compute 10,000 samples. But for the traditional method based on K expansion, a single sample takes about 7,000 seconds. Therefore, in fact, the ratio of the computational cost is also like in the order of 10 to the power 4, and the big computational cost saving is also seen here. This is some reference for the PDE solver for this stochastic elliptic equations. In the future, we want to extend our work in other net applications. This is the image segmentation problem, and this is the eigenvalue decomposition of this. This is the eigenvalue problem for a Schrödinger operator in quantum chemistry. Both of them are involving with eigenvalue problems, and both of them prefer localized eigenmodes. Therefore, they have some similarity with our problem, but also they are different because now we don't need to approximate the operators, we only need the physical modes. Therefore, we need to modify our methods a little to apply to this kind of problems. This is the end of my talk. Thank you.